Now that we've studied some simple growth decay models, we are going to move on to more general linear differential equations. And I want to begin with an example that is going to motivate a technique that we will use to solve linear differential equations. So here we have the differential equation y prime plus y equals t plus 1 with an initial condition that y of 0 equals 1. Now at first glance, there doesn't seem to be a guess that we can use for the solution, and there doesn't seem to be a straightforward technique to figuring out what y is. So what I'm going to do is manipulate this equation a little bit to put it in a form that we can solve it. So I'm going to multiply both sides of the equation by e to the t. Now this may seem mysterious right now, but I promise you that I'm going to motivate this technique in a little bit. So e to the t times y prime plus e to the t times y then equals t plus 1 times e to the t. Now what I want you to see here is that e to the t times y prime plus e to the t times y is actually the derivative of e to the t times y. What I've done is I've reversed the product rule. So if I was to take the derivative of e to the t times y, I could leave the first alone, e to the t, and take the derivative of the second function, which is y prime. And then I would add to it the derivative of e to the t, which is e to the t, and then I would leave the y function alone. And so you can see I've sort of undone the product rule on the left-hand side of the equation. Now the right-hand side is going to stay the same. It's still going to be t plus 1 times e to the t. Well, now what I'm going to do is I'm going to anti-differentiate both sides. Okay, so essentially, if the derivative of e to the t times y is t plus 1 times e to the t, then e to the t times y should be the antiderivative of t plus 1 times e to the t, dt. And so that tells us that e to the t times y is equal to, okay, what is it equal to? I'm going to have to do a little bit of integration by parts. Okay, so here I'm going to let u be t plus 1 and dv be e to the t. And so that tells me that the integral is going to be u times v. So it's going to be t plus 1 times v. V is the antiderivative of e to the t, which is also e to the t. And then that's going to be minus the integral of v, which we know is e to the t, times du, which if I take the derivative of t plus 1, that's going to be 1 dt. At this point, you're all familiar with integration by parts, so I believe that you could work out that integral yourselves offline. Okay, so let's keep going here. This tells us that e to the t times y is equal to t plus 1 times e to the t. And of course, the antiderivative of e to the t is, again, e to the t. And I'm going to add some sort of constant. Okay, so that tells me that e to the t times y is equal to t e to the t. And then I would be adding e to the t and subtracting e to the t. So those go away. So I'm left with plus c. So now I can solve for y. Y is equal to t plus, when I'm dividing by e to the t, that gets rid of the e to the t there. And then I'm going to have a c e to the minus t. And that gives me y. Now I want to match the initial condition, so I want to point out that y of 0 is equal to, in this case, it's equal to c, but y of 0 is also supposed to equal 1. So that tells me that y of t in this case is equal to t plus e to the minus t. Now, I encourage you to take this solution and substitute it back into the differential equation and check to see that that's actually the correct answer. But for now, we've solved this linear differential equation. But hopefully, you've had some questions along the way. One of these questions is, why is this differential equation called linear? Another question is, why did I multiply both sides by e to the t? How did I know that that was going to allow me to rewrite the left-hand side using a product rule? So in order to understand that, we need to understand a little bit more about linear differential equations. So what is a linear differential equation? Well, a general first-order linear differential equation is a differential equation of the form dy dt plus p of t times y equals q of t. So let's go back and look at our example for just a moment. Okay, so we have a dy dt. Okay, then we have a p of t times y. In this case, p of t was 1. And then on the right-hand side, we had a q of t, and q of t was t plus 1. So the differential equation that we solved was linear. It was of that form. Okay, so what makes it linear? Well, I'm going to rewrite this equation a little bit differently. I'm going to rewrite it as Ly is equal to q of t. And L is everything that's being done to y. So what is being done to y? We're taking the derivative of y, and we're also multiplying y by p of t. Those are the things that we're doing to y. So why did I call it L? Well, L, in this case, is a transformation. And in particular, that transformation is taking the derivative of y and adding a multiple of y, that multiple being p. And that transformation is linear. So essentially, what I'm doing to y on the left-hand side of the equation is a linear transformation. And that's a linear transformation in the sense that you learned in your linear algebra class. So what does it mean to have a linear transformation? What needs to be true for a linear transformation? Well, if you remember, if you do a linear transformation to the sum of two vectors, say y1 plus y2, then it should equal L done to y1 plus L done to y2. Okay, so is that going to be the case? So I'm going to do the derivative plus p to y1 plus y2. And you're thinking about y1 and y2 as being two vectors in our vector space. What is our vector space here? Well, it is the vector space of differentiable functions. So if I take d dt plus p done to y1 plus y2, that's going to be dy1 dt plus p times y1 plus dy2 2 dt plus p times y2. Okay, so that is L done to y1 plus L done to y2. So essentially, L is linear in this case because the derivative operator, ddt, is a linear operator. We know that the derivative of the sum of two functions is the sum of the derivatives. And then multiplication is a linear operator. It distributes, okay? P times y1 plus y2 is py1 plus py2. Okay, so that's just the first part. Okay, what happens when we do L to a constant multiple of y? Okay, so we're going to do d dt plus p done to a constant multiple of y. Okay, so that's d dt done to cy plus p times cy. And that is going to be c dy dt plus c py. Okay, so that's actually going to be c L done to y, because we can factor out the c. Okay, so we've satisfied the two properties to show that L is a linear transformation. Okay, so that's what's making this equation, this first order equation, a linear differential equation. The fact that the transformation, what is being done to y, is a linear transformation. Now, there are two types of these linear ordinary differential equations. Okay, there's going to be the homogeneous and the non-homogeneous. Homogeneous equations are when q of t is equal to 0 for all t. So if what's on the right-hand side is identically 0, then that's called a homogeneous equation. Non-homogeneous equations, okay, that's when q of t is not equal to 0 for some t. So if there's some point at which the right-hand side is not 0, then it's called a non-homogeneous equation. Okay, now we understand why the example that we solved was a linear equation, but we don't understand why multiplying by e to the t helped us solve the equation yet. Okay, so the next thing that we want to do is to figure out how to, what integrating factor we can multiply this equation by so that we can actually solve it. So we have our equation dy dt plus p of t y of t is equal to q of t. And I'm going to suggest that we always want to multiply this equation by mu of t. So this is the Greek letter mu, and mu of t is always going to be the e to the antiderivative of p of t dt. So that looks a little bit mysterious, but we're going to try multiplying our equation by mu of t so that hopefully we can see that we can more easily integrate this equation. Now, the advantage of multiplying by that integrating factor mu of t is that when we take the derivative of mu prime of t, well, that should be, again, the exponential e to the p of t dt times the derivative of what's in the exponent, and that's going to be p of t. So essentially, the derivative of mu is p of t times itself, mu of t. Okay, so we're going to multiply both sides of the differential equation by mu so that we get mu of t times dy dt plus p of t mu of t y of t, and that's going to equal mu of t times q of t. Now what I want you to see is what is on the left is actually a product rule. What is the derivative of just mu times y? The derivative of mu times y using the product rule is going to be mu of t times the derivative of y, dy dt, plus mu prime of t times y of t. Okay, so that's mu of t dy dt plus p of t, because mu prime of t is p of t, mu of t, y of t. And so hopefully you see that this matches the right-hand side of our equation. So we can rewrite our differential equation as d dt of mu of t y of t, because that's truly what is on the left-hand side, is equal to mu of t q of t. And now we have that the derivative of a function on the left is equal to mu of t q of t. So that tells us that mu of t y of t must be the antiderivative of mu of t q of t dt. Now, I'm going to explicitly add the plus c here, just so that you can see what kind of happens with the final step. Okay, so when I want to find y of t, I can divide everything by mu of t. So I'm going to get 1 over mu of t times, okay, the integral of mu of t q of t dt plus c. And now I've found a solution for y of t. Okay, oftentimes though, we're going to be given an initial condition. And if we're given an initial condition, there's kind of a nice way to carry out this step right here. Okay, so it's to integrate both sides. So I'm going to integrate from 0 to t. And what do I need to integrate? Well, I'm not going to write d dt because I need another variable there. So I'm going to write it as d ds mu of s y of s ds. And then that's going to equal the integral from 0 to t of mu of s q of s ds. So I'm going to integrate both sides using a definite integral this time because I have this initial condition I can work with. Well, if I integrate the derivative of mu of s, y of s, then I'm just going to get mu of t, y of t. That's evaluating the antiderivative at t, but now I'm going to subtract mu of 0, y of 0. And then that's going to equal, again, the integral from 0 to t of mu of s q of s ds. Now, y of 0 has a name. We're going to call it y sub 0. Okay, so again, I'm going to move this to the other side of the equal sign. And then I'm going to divide by mu of t. So y of t in this case is going to be 1 over mu of t times u of 0 y sub 0 plus the integral from 0 to t of mu of s q of s ds. Okay. And so that gives us the general technique. Okay, we need to multiply both sides of the equation by an integrating factor. That integrating factor, we're going to call it mu, and it's always e to the p of t dt. E to the antiderivative of p of t dt. Okay, so that's the integrating factor that we're always going to multiply by. Okay. So let's start looking at just a couple examples. The first example is t times y prime plus y equals cosine t. And the first thing that we need to recognize is that this is not in the same form that our equation was before. We needed the derivative to be by itself. We're supposed to have y prime plus p times y. So I'm going to divide everything by t. So y prime plus 1 over t times y is going to equal 1 over t times cosine of t. So that means that mu is going to equal e to the antiderivative of 1 over t dt. The antiderivative of 1 over t is going to be natural log of t. And e to the natural log of t, of course, is t. So that's telling me I should multiply both sides of the equation by t. Okay, so I'm going to get ty prime plus, t times 1 over t is 1, so I'm going to get y equals cosine t. Oh, I'm back to where I started. So that means that what's on the right-hand side must have been a product rule anyway. And in fact, it is. It's the derivative of t times y. So remember here that it's always going to be the derivative of mu of t times y. And in this case, mu of t is t. Okay, so that's going to equal cosine t. And so now I just need to integrate both sides. Okay, so I did this integral last time as an indefinite integral with a plus c. So this time I'm going to do it as a definite integral to kind of show you that technique. So I'm going to integrate from the starting time, which in this case is pi over 2, and to the ending time, which in this case is going to be t. And I'm going to integrate d ds of s times y ds, and that's going to equal, let's see, the integral from pi over 2 to t of cosine of s ds. Okay, so doing the left integral, the antiderivative s times y, the antiderivative of the derivative of s times y is just going to be s times y. So I'm going to evaluate this. I'm going to get t times y of t minus pi over 2 times y of pi over 2. Now y of pi over 2 happens to be 1 from our initial condition, so that's how we plug that in. And then I'm going to anti-differentiate the cosine of s to get sine of s, and that's going to be evaluated between pi over 2 and t. So I'm going to keep this going. So I'm going to get that t times y of t is equal to, I'm going to go ahead and bring the pi over 2 to the other side. And then plus sine of t minus sine of pi over 2. Sine of pi over 2 is just 1. So y of t, in this case, is going to equal 1 over t times sine of t plus pi over 2 minus 1. So that is our solution. Now, I challenge you to, again, substitute this solution into the differential equation, okay, to make sure that it satisfies the differential equation and then it matches the initial condition, okay? Something that I want to point out about this solution is that this solution is not continuous at t equals 0. And this is an issue because I'm supposed to be able to take the derivative of this solution. And if it's not continuous at 0, then it's certainly not differentiable at 0. Okay, so this solution is supposed to be differentiable at 0. Okay, so it must be differentiable. So because it's not differentiable at t equals 0, okay, the solution only exists when t is not 0. Okay, so what I'm going to do is I'm going to pick the largest interval that I can that includes my initial condition, which in this case is that t must be between 0 and infinity. And I know that my solution exists on that interval. Now, if my initial condition had been with a negative t, I would have picked the interval from minus infinity to 0. But my initial condition was at pi over 2, and so I want to include that initial condition. So this solution only exists for between 0 and infinity. Okay? I don't say that it exists for negative time because the solution can't cross that discontinuity. It has to be differentiable. So it only exists between 0 and infinity. Okay, we're going to do one last example, and that is the equation ty double prime, or ty prime plus t plus 1 times y is equal to 1, and y of natural log 2 is equal to 1. Okay, again, it's not quite in the form that I want, so I'm going to divide by t, so I get y prime plus, let's see, 1 plus 1 over t times y is equal to 1 over t. Okay, so I need a integrating factor, mu of t, and that's going to equal e to the antiderivative of 1 plus 1 over t dt. Let's see, that's going to equal e to the t plus natural log t when I take the antiderivative. I'm going to rewrite that as e to the t times e to the natural log t, because e to the natural log t is t, and then I still have just an e to the t. So that is my integrating factor. So I need to multiply both sides of this equation by t e to the t. So what I'm going to get is going to be t e to the t times y prime plus, multiplying by t e to the t, I'll actually get t plus 1 e to the t times y is equal to e to the t. And then the left-hand side, I can rewrite using the product rule. So it's actually the derivative of t e to the t times y. It's the derivative of mu times y. And I really encourage you to take the derivative of t e to the t times y using the product rule so that you can see that I've written this correctly by undoing the product rule. Okay, so this is equal to e to the t. I'm going to go back to my original version of doing the problem. I'm just going to anti-differentiate both sides. So t e to the t times y must be the antiderivative of e to the t, dt. So that tells me that t e to the t times y must equal e to the t plus c. And now I can solve for y in this case. So y is equal to 1 over t when I divide e to the t by t e to the t plus c over t e to the minus t. Okay, so now I'm going to move on with my initial condition. Okay, so I'm going to plug in the initial condition. Sometimes I write IC for initial condition. Okay, so y of natural log of 2 is supposed to equal 1. So then 1 is supposed to equal 1 over natural log of 2 plus c over natural log of 2 e to the minus natural log of 2. Okay, so I'm going to multiply everything by natural log of 2 here. So natural log of 2 is going to equal 1 plus c e to the minus natural log 2. So that's going to be e to the natural log 2 to the minus 1 power. Okay, so natural log of 2 minus 1 is going to equal, let's see, c times, that's going to be e to the natural log 2 to the minus 1 power. So the e and the natural log cancel. 2 to the minus 1 is a half. Okay, so c is equal to 2 natural log 2 minus 2. Another way to write that is natural log of 4 minus 2, if you like. Okay, so what is y of t going to be in this case? Y of t is going to be 1 over t plus 1 over t times c, which is natural log 4 minus 2, and then times e to the minus t. Again, I want you to notice that this solution does not exist for all time. It only exists when t is not 0, or the interval containing t, or the interval containing the initial condition of natural log of 2 that doesn't go beyond 0. So this only exists for 0 less than t less than infinity, okay? Because it does not exist when t is 0, and so I'm going to pick the largest interval that contains my initial condition of natural log of 2 that doesn't go beyond 0. Now, I suggest that you use this technique on your own to solve one more differential equation that we've solved already, okay? And so I'll just write this note right here, that one more equation that I think you should all try to do on your own as an example is y prime equals ay plus b. We've done this one on our own, and y of 0 is going to be y sub 0. Try doing that on your own, okay? You might want to rewrite the equation as y prime minus ay equals b, and solve this using integrating factors so that you can see you'll get the same solution that we did using our guess and check method.